And we're live. Hey guys, this is Jan from DoraHacks, and welcome to the workshop of our Hack AVS workshop series. Today is workshop number 5, and it's about the Polymer workshop. And before we start, let me give you some background on this hackathon. As the largest Web3 multi-chain developer incentive platform, it's an honor for DoraHacks to support the Hack AVS empower the Eigenlayer restaking ecosystem hackathon. And we're looking forward to seeing all the incredible projects building on top of Eigenlayer. So today we have here Ken. He is technical growth manager at Polymer, and he will do a workshop. So for the audience, if you do have any questions in the meanwhile, feel free to drop them in the comment section and we can answer them towards the end of this workshop session. So without further ado, Ken, whenever you're ready, feel free to start.
Awesome. Yeah, thanks for the introduction. Hey, everybody. My name is Ken Miyachi. As Jan mentioned, I'm Technical Growth Manager and Solutions Architect at Polymer. And I'll be presenting, about Polymer today and how this fits into AVS and what Eigenlayer is building as well. Definitely feel free to comment, ask questions. I'll try to answer questions like live. I think it's oftentimes a lot better and more fruitful for everyone if there's interaction and people are asking questions. So yeah, I'll get it started. So the goal of Polymer is to bring scalable on-chain networking to Ethereum. And so how does it do this? So essentially it's bringing the IBC network to Ethereum, and it's doing this through a OP stack L2, which uses Eigenlayer DA. It has Ethereum settlement, and it brings Cosmos SDK's interoperability features to Ethereum. And so one way to think about it is, from the Cosmos ecosystem, Ethan Hunt and Sam Hartman, I think, coined this term of a port city. And essentially, a port city is a clearinghouse for trade routes to the largest economies in the world. Alexandria was an ancient port city that connected Egypt to Africa, Europe, Asia, etc. And then a more modern example is the Port of Los Angeles, which connects kind of the US domestic trade routes to many of the economies around the world. And the goal of Polymer is to be the port city of the Ethereum ecosystem, to connect all the different components of Ethereum, all the L2s, and eventually L3s, and then even beyond the Ethereum ecosystem. That's the vision. What we're starting with is interoperability between OP stack L2s, and then progressively and iteratively expand over time. So how does it do this, right? The two core pillars of Polymer's technology are IBC transport and Ethereum settlement. So Polymer is extending the IBC protocol to all chains that don't come with IBC built in by default. So all Cosmos chains have IBC built in, but Ethereum doesn't have IBC built in by default. So it is extending IBC's functionality to Ethereum chains. And what it's doing is it's separating the transport level execution of IBC with application specific logic on each of the rollups or each of the chains themselves. And then for security, it relies on Ethereum settlement. So Polymer has an IBC client for OP stack rollups, which essentially checks proposals of all the rollups that are made to the Ethereum L1 to ensure and verify the state of all the rollups that are interacting with each other to ensure that there's correct transactions being sent to one another. And so what this is really doing, as I just described, is just really extending the native bridge of Ethereum. So, the native bridge is essentially a bridge that all the L2s have to use, essentially bridging assets and information, messages from the L1 to an L2 or any rollup. And so Polymer is extending this by reading the state of the L1, looking for proposals that are made from each L2 and using that information to verify transactions and relay data between rollup to rollup. And this is just a brief diagram showing, right, if you see on the left bottom side of the graph, the state is being read by Polymer, using that information to verify the transactions, and then relaying the information from rollup A to rollup B. And I'll go into a little bit more detail about kind of this process later on. So how does Polymer bring IBC to Ethereum? So, oh, did I skip a slide? Oh, sorry, I skipped a slide. So, okay, why is IBC important? So there's many different transport protocols or interoperability solutions out there. IBC is battle tested and mature enough. It's been around since 2021 and has produced over 1 billion of transports or transactions between chains. And over the course of 3+ years, there has been a total of 0 exploits of the IBC protocol itself. And what that really boils down to is just the fundamental design of IBC, which consists of sending, receiving, and acknowledgement. So many other interoperability protocols establish a line of communication that goes from chain A to chain B, or source to destination. I think something that has made IBC significantly more secure than some other solutions out there is this really concept of acknowledgement. When you send information, a packet, a token from a source to a destination chain, for the full lifecycle to complete, an acknowledgement transaction needs to be sent back from the destination to the source chain to ensure and verify that the message has been received. And this has gone a long way in essentially reducing the number of exploits that have happened over IBC, among a variety of other things. Okay, so I just went over why IBC is important, some of the amazing value propositions of IBC. But right, IBC is written, if you're familiar with the Cosmos ecosystem, there's IBC Go, there's a Rust implementation, but right, how does Polymer bring IBC to Ethereum? Polymer has implemented something called vIBC, which is smart contracts that essentially implement the IBC spec in Solidity. And what it does, as I mentioned before, is it decouples this transport layer of IBC from the connected chains that it's associated with. And so what this is really doing is the goal of this is to bring the value propositions of IBC to any chains that don't have it by default. And so you can deploy these vIBC contracts on any EVM-based chain and then are able to interact as long as Polymer needs added to. There's a couple of other steps to fully integrate. And so going into this a little bit, so right, I talked about the importance of IBC and essentially verification. I think there's been a lot of the security vulnerabilities and exploits have actually happened through bridges over the past couple of years. And I think that is because when you're interacting on blockchains, oftentimes the focus is on both performance and cost. And so to save on performance and cost, oftentimes you have to sacrifice security. And so there's a variety of different ways which existing bridge security models rely on, where you have, pre-confirmations, different steps of pre-confirmations that improve the performance and the cost of sending cross-chain transactions. And this is just a brief overview outlining some of the different layers of kind of security and performance that you need for kind of full verification, and then bucketing them in some of these different categories of unsafe sequence pre-confirmations, safe sequence pre-confirmations, finalized sequence pre-confirmations, and verified soft confirmations, which have different, essentially, security models, but also have very drastically different performance specifications as well. So you can see basically, as in the most unsafe security model, you can verify and finalize transactions in 3 to 10 seconds, with maybe the most secure being, hey, for at least optimistic rollups, waiting for the 7-day fraud-proof window to finalize and then sending the transaction. And so there's been a shift towards modularism and an emergence of layer 3s, and even more and more L2s are popping up day to day. And in this kind of modular model, the L1, the Ethereum L1, is serving as the kind of security layer of this entire ecosystem. L2s are very focused on scale, and L3s, at least it's theorized and work is starting to get done there, will be focused on application-specific logic. So in Web 2, a service mesh is a software layer that is connecting different microservices and applications. And the goal of Polymer is to become the service mesh that is connecting this diverse array of L2s and L3s very seamlessly, where the end user doesn't have to know about it. And maybe to provide an example here, like when you go to Amazon.com and you add to cart and you check out and then you click purchase, those are actually separate microservices that are all communicating together in a seamless fashion that create an amazing user experience. So the idea for Polymer is to create a similar service mesh orchestration framework around these different microservices, but for Web 3, in this case L2s and L3s, that can interrupt seamlessly and create amazing user experiences. So going into a little more about how this works and kind of like bringing it back to some of the points I was talking about in the beginning about Ethereum settlement. So on Polymer, right, every rollup, the state of every rollup is read from the Ethereum L1 and maintained on Polymer Hub, which is itself an OP Stack L2. So, right, all these different components that you see, right, every single rollup is writing to the Ethereum L1, writing proposals and writing their state to the L1. Polymer is reading that state and storing it in their L2. What this means is that the state of all these different L2s across the Ethereum ecosystem remain in sync and stored in the Polymer Hub. And what this does for interoperability is it introduces a novel approach to communicate as being the first hub and spoke interoperability solution for layer 2s. How this differentiates from some existing solutions is that many of the current interoperability solutions and bridges rely on one-to-one connections and mappings to one another. And in this case, in this kind of technical design and architecture, right, if you wanted to add a new rollup, you would need to just connect to the Polymer Hub, and then you would have default connectivity to all of the other rollups that were previously connected. And so what this really does is it allows to simplify and streamline connectivity without exponentially increasing the complexity of interoperability. So if you can imagine, let's say you have 10 connected chains and you want to add, number 11 of the connected chains to a network. And many solutions, now you have to create 10 new connections from the new one to each of the existing connected chains in the network. In Polymer, as long as you create a single connection from this new chain to Polymer, then those connections are created by default. So going into kind of this network topology and how everything works. So kind of as I just mentioned, the state is read from the Ethereum L1, and right, is stored on Polymer, and that is the verification. In Polymer, verification is separated from the coordination or the actual message passaging that enables dApps to talk to each other and actually have control over their own network topology. So this is contrasting, just as many of the other design principles from other existing interoperability protocols, but is very similar to actually current microservice application development frameworks, and is very much aligned with service meshes. So in this case, right, dApp developers can create their own pathways between applications on different chains, or use a universal channel that is established just between chain A and chain B. And what this does is it gives dApp developers complete ownership and control over their interoperability and network topology. And it gives that control allows you to have exclusive both performance and security for your specific application. So an example that I often use is if you're transacting very high, like critical or high value transactions cross chain, you may not care as much about the performance as you do about the security, and you want to create like basically the most robust security model around it, and maybe rely on Ethereum settlement. And so it can take longer, but because you're transacting very high value information, that's the security model and performance that you're choosing and optimizing for. And in contrast, if you are just sending messages that don't have any value attached to them, then maybe security is a lower kind of a lower criteria for you, and what you really care about is performance. And you can optimize and create virtual pathways on these different security and performance optimizations. And so, like, in summary, right, Polymer is the aggregated state of Ethereum rollups, and it uses IBC compatibility. It uses IBC to create compatibility between these chains. It uses, what this does is that because it has an aggregated state, it enables these rollups to essentially seamlessly be part of a single ecosystem that can create amazing user applications. And then one point to make is that this state can be used to also enter different ecosystems beyond Ethereum, which is like a future goal and the vision of Polymer down the line. So this is Hack AVS. Right, and so how does this relate to EigenDA, or how does this relate to AVSs? And so I would say, like, where I would start with is that, as I mentioned in the original slide, introduction of Polymer, Polymer will use EigenDA as their data availability solution. And so EigenDA is an AVS itself, and the reason to use EigenDA is because it's scalable, secure. It has cost improvements, but then I would say the main one is that it is Ethereum centric. The security model of Polymer and the interoperability solution that Polymer built is essentially relying on reading the Ethereum state to verify state between these different rollups so that transactions can occur in a secure manner. And so by using EigenDA and the fact that EigenDA is Ethereum centric, the settlement still actually occurs on the Ethereum chain and is very aligned with the vision of what Polymer is trying to build. And so there's a variety of different other use cases beyond just data availability that Polymer could use an AVS for. I think some of the most interesting use cases come in the term I didn't move forward here. Some of the most interesting use cases come in the form of authorization. So you can think of a multi-sig authorization of an AVS node of operators, where you're just enhancing the security of cross-chain transactions by having an operator pool basically register on different multi-sigs on each chain that have to sign cross-chain transactions to enhance the security, and maybe they could get slashed or some negative recourse could happen to incentivize them to essentially only sign correct transactions. Some of the other two that are very interesting are both batching services and data indexing authorization services. So I think this is more on the performance improvement side. So you can think of, hey, could an AVS be in charge of batching transactions from chain H and chain B, or be in charge of, in control, essentially indexing data from multiple different chains in an off-chain data store, where essentially, right, you're trying to improve either both the performance of cross-chain message passing by batching, or improve the recall and indexing of data that is sent between chains by storing that off-chain somewhere. And these AVS operators could essentially be performing this off-chain logic that either batched and or wrote the information off-chain. And so let's see, there's a brief demo that I usually show of like what it means to really abstract and some of the powerful aspects of kind of abstracting away the complexity of developing interoperability applications. But I'm not sure if I have access to share. But essentially, right, interoperability is just really hard on the developer. And there's this concept of chain abstraction, which the definition of is that when a user is, using an application, they don't really know what blockchain they're using, or even that they're using blockchain at all. And so by definition, really, chain abstraction is on the user. And so, however, this makes it very difficult on the developer. For a developer to create currently a cross-chain application, they need to, deploy their smart contracts on multiple different chains, create the connections between those applications on multiple different chains, and then manage, all the different contracts in these different environments. And that is extremely, extremely difficult. And so, if you go to this repo, you basically, install some npm packages, and then you run a script, and it sends a packet, and it's a basic example of a counter. Excuse me. That sends message from optimism to base and acknowledge it back. And so it shows like what Polymer is trying to do is create a much better developer experience to develop, multi-chain applications. And so I'm going to go briefly into what I had here. So kind of like, what are the steps to what would be the steps to develop an AVS? So it's like, as mentioned, I see in some of the comments, Eigenlayer introduced this paradigm shift by introducing restaking. And in this modular ecosystem, I talked about different L2s and L3s. Now different components of actually what was considered a blockchain are now being separated into different components. And validation is, at Polymer, we think as a super critical point to ensure in this modular ecosystem, to ensure that, and in interoperability, to ensure that and verify cross-chain transactions. And so what kind of transaction validation means is DA confirmation, is the data there, and Ethereum verification. And so the idea that we had for this hackathon or anything else is to create a server or light client that had valid data from Eigenlayer DA for L2 transactions. And then, maybe can open it up to any questions. I'm only able to see. Yeah.
So let's give the audience some time to digest the information you provided. I think it was pretty insightful. What's the best way to reach out if there's any questions asynchronously?
Yeah, so highly recommend to reach out. Like our Discord is where most of our developer ecosystem lives. So definitely scan this QR code, join our Discord. Definitely really active. We're actively running different challenges and tests. Our GitHub's right here, and our Twitter is also in this QR code. And then also feel free to reach out to me directly, and I put my Telegram and Twitter handles below.
Okay, perfect. Maybe you could also share a bit more specifically what you would like to see that's being built at the AVS hackathon.
Yeah. So I think like the first place to start, I think, is really maybe on this first kind of idea of a multi-sig authorization AVS node. So the idea would be have an AVS contract, very simple, create something in Solidity that was a registration for any address, and operators would be able to register and then sign, and that would just be tracked by the AVS of who signed what transaction, and then basically on any kind of malicious behavior or incorrect behavior, implement some sort of slashing mechanism that would disincentivize the operators from signing data that should not have been sent or was malicious.
Okay, guys, so you should build something like that. Is there anything else you would like to add or mention that you didn't mention before?
Yeah, I mean, I think, right, Eigenlayer talks about it a lot, but like, right, AVSs enable any arbitrary off-chain data to, add crypto economic security around any arbitrary off-chain logic. So very open to new ideas of how to use an AVS to integrate with cross-chain transactions and interoperability. And so I would say definitely don't be scoped by these ideas, and very open to chat and discuss any interesting ideas that the community has.
Yeah, that sounds very good. I'm also looking forward to seeing innovative approaches, something that's new. All right, so thanks a lot for your time today, for the great workshop. It was super insightful, and I think the audience has learned a lot. For the audience, feel free to ask or join their Discord, ask some questions over there. There will be also more workshops, so like if you haven't subscribed to our socials, feel free to subscribe to our Binance Live and YouTube. So thanks a lot, Ken, for doing this incredible workshop today, and see you soon.
Awesome. Thank you.
All right. Take care. Thank you.